This lab explores constant velocity motion, the motion of an object with a constant speed moving in a constant direction. By analyzing a recording of an object moving at the same speed in the same direction, I used Tracker to plot its motion on the x-axis over time. This visual of observed motion can then be used to create a computational model depicting an object in motion with a constant velocity and zero net force. I then compared the experimental observations to the computational model to see if my model matched what actually occurred. The fundamental physical principles of this lab experiment include Newton's first law, stating that an object in motion will stay in motion unless acted upon by forces in its surroundings, as well as Newton's second law, which allows us to calculate the expected future position of the object given the forces acting on the object. In the case of this experiment, our computational model assumes constant velocity. As shown here, when the velocity is constant, the net force is equal to zero. I began by setting the blue tracker calibration stick length to 0.238 meters, the length of a standard basketball. I then set the coordinate axis at the initial center of the ball with a degree tilt of 1.2 degrees to match the angle of the recording and that of the table the ball was rolling on. I then used Tracker to quantify the x-axis position at equal time intervals. Using the x-coordinate for the ball at time 0, I calculated the ball's initial position. Using this data point and the x-coordinate for the ball at time 0.033 seconds, the second timestamp, I then calculated the initial velocity. I altered the code to reflect these vectors for the initial conditions. I then inputted the mass of the ball, the value of which did not affect the outcome of the model. Finally, I altered the overall time of the simulation to match that of the analyzed video and changed the total net force to 0. This is the key part because when the code calculates the position and velocity at each point in time, the velocity will remain constant and only the position will be updated. Here we see the outcome of the coding, the computational model of motion of the object. Having used Tracker to mark and record the x-coordinate of the center of the ball at 28 sequential frames, I created a graph of the observed position values over time. Then, using the computational model in GlowScript, assuming no net forces, I found the calculated x-coordinates of the object's motion assuming zero net force, as seen in the previous video. I then added the modeled positions onto the same graph shown here and compared the results. The graph here shows that the ball did not roll as far as expected, indicating that the constant velocity motion model is not exactly matching the experimental results. The question was posed as to what would happen if the axis orientation was flipped. As seen here in this graph, the position magnitudes would be the same, but they would be negative instead of positive. This would alter the overall velocity in that it would have the same magnitude but be negative. This is seen in the negative slope of the graph. The computational model of this experiment assumes that there is a zero net force. However, that doesn't mean that there are zero forces acting on the object, rather that they cancel each other out. If we were to estimate the total number of pushes and pulls on the ball, we would evaluate first the initial force given the object motion, air resistance and friction in the direction opposite the object's motion, and finally, the weight force due to gravity and the normal force from the table canceling the weight force out. Because the velocity is nearly constant, we make this assumption that all forces present cancel each other out so the velocity remains constant. The results showed that the velocity did not remain perfectly constant, indicating that not all the forces were canceled out, or that the initial velocity selected was faster than the average velocity over the total time period. In the future, a smoother ball could be used to reduce friction, or a smaller time period could be selected. Despite the slight difference in slopes, the computational model is a very close fit, showing that our model is a good analysis for the experimental observations.